Good morning, I'm Kenneth Marentes. This is
Miranda.
Jerry Pico.
We're going to be presenting our senior design project on multipurpose autonomous buoy. So a quick description of our problem statement. We're going to be creating an autonomous buoy that's GPS guided. It has to be weatherproof due to the fact that it's operating in water. We wanted to make it economically feasible, and we wanted it to be used in various applications. Our motivation to do this project, when we were looking up different types of smart buoys, we noticed that a lot of them were very bulky and hard to transport. Also, they were very expensive. They were mostly used by large research institutes and large companies. We wanted to integrate state-of-the-art technology into marine equipment and also help in the surveillance and preservation of marine sanctuaries. So for our proof of concept, we're focusing on a diving flag. There's no technology integrated with diving flags. It's just a flotation device, a flag, and a tie. With our design, we hope to eliminate that tie between the diver and the diving flag, and have our system capable of detecting life-threatening situations. So for our goals for our project, we wanted to make it as portable as possible. We wanted to have an autonomous mode that can maintain a locked GPS location or follow a set GPS route, so it will circle around a certain place. We wanted to have a manual mode, so you can use a remote controller. The user on the boat could also use the camera adapter to attach a camera to see what's going on underneath the water or above the water, depending on where you place it. And we wanted to achieve a competitive sales price. So a quick literature survey of what we found. This is the Chesapeake Bay Interpretive Buoy System. It's a system of buoys that are anchored, and they provide information to the public via Wi-Fi. Users can access each buoy, and they can get historical information regarding oceanography and meteorology. The Optus Clever buoy is a system of buoys in Australia used to protect beaches from sharks. It's equipped with state-of-the-art sonar to detect shark movement, and when it does detect shark movement, it tells the closest lifeguard tower so that they can alert beachgoers. Next is a Pen Air Smart Monitoring Buoy System. It's a free-floating system that's highly customizable, and they sell it in various sizes, which is what we try to achieve too. The Offshore Power Technology Buoy is a very large buoy. It's approximately like 150 feet in length, and it's used to harness the energy of the waves that occur off the shore of Oregon.
So here we're entering our first design prototype. Our initial concept was a spear, and it was more of a passive system. It would stay in one area, and we quickly discovered how easy the waves would carry it away and take a hold of it. We moved on to a more catamaran style, which, as you can see, it's closer to what we ended up with. Higher up off the water, so more of the hull is in the air and not in the water itself. And our last prototype was a alternative. Is fully submerged. Only the flag was visible, and the entire unit itself was under the surface. Moving on to our final concept, we ended up with a more of a catamaran style. As you can see, we have two balsa wood pontoons attached by an aluminum frame with the electronics and the power unit in the center. Here you can see our final design. We have our motion sensors on top, our electronic box, and our power system in the bottom, which is also a wet, dry system. Here's one of the simulations. This is moving at our max speed of 2 meters per second. This shows here the pressure caused on the hull by water and velocity. As you can see here, most of the pressure is located by the front, and in the rear, you will see a vacuum area, which for the future improvements we plan to reduce, which will take care of efficiency. Here you can see a cross-section of the pontoons. There's ribs stationed across the hull itself, and across the sides, there's long ribs on the actual skins.
So the main sensors and components that we're using in our project are the Arduino Uno as the brain of our project, the I2C GPS shield, which was made just for the Arduino Uno, so it's easy to use. We have 4 ultrasonic motion sensors for our detection system, and a tilt compensated compass module, which works with the GPS for our automated system.
Here we enter our construction. This is our top surface. and visible rib here on the sides. This is our jig for setup. This is how we use a marine adhesive, which is also a sealant. We have both pontoons being assembled. In general, for our pontoons, they're marine sealant on the inside. On the outside, we use a wood sealant first, which is not pictured, followed by polyester urethane coat on the outside to give it its color and prevent it on any salt spray damage to the wood.
So the electronic setup, we have two batteries powering everything. The first battery is powered the Arduino that's connected to the GPS shield. It's also connected to the compass module and the speaker. The two LEDs, the green LEDs for GPS lock and the red LEDs for the detection system. And then we have the Adafruit, which adds a lot more outputs and inputs. So then from there, we have the second battery connected to the Adafruit. And then we have the voltage regulator, the ESC, the switch to turn it on and off. We have the motor, servo, the 4 sensors, and the micro receiver connected to the control. And that's the electronic setup. And then for the housing for electronic setup, we have this. We had initial designs, but instead of making one, we just bought one from the store, and it was more than enough. And this houses all the electronic parts, which is that are not waterproof. As in the waterproof case, we have both batteries. The second battery is not shown. We got the Arduino, the GPS shield, Adafruit, compass, and pretty much everything that's not waterproof. The second housing, we 3D printed it, and because we bought this from the used RC boat, all the parts were waterproof, so we didn't mind it touching the water, and that's why we have it underneath. The programming, so we have 4 programs. The first one's manual mode, so you can use it. The detection system is off, and you can have a live video feed via Bluetooth with GoPro. Obviously, you have to buy the GoPro. The second program, the GPS will lock, and then as it floats away from the waves and currents, it'll come back into the spot, and then the detection system is on, so that way if the boat gets too close, the LED will turn on and the speaker will go off. The third program is about the same thing. The GPS will lock, but instead of staying still, it will go around a circle, so that way the diver can go down, and at least the pontoon, the boat, can go around a circle, protecting the diver. The third program, the GPS will lock. The fourth program, the GPS will lock. The fourth program, actually, you give the GPS locations, and then the buoy will actually follow the locations that you give. This is a quick with control. Pretty much it has a bunch of switches. So the first switch will give you all programs. You got program 1, program 2, program 3, and it can handle up to 9 programs. So we like to be able to implement more programs into it.
Now, one of the most important tests that we had to do was a buoyancy test. We found that the total weight of our components was around 15 pounds. So we calculated the theoretical buoyant force that would result if 50% of our vessel was submerged to be 16 pounds of buoyant force. So to test this, we tested each pontoon separately. We put the pontoon in a bathtub, and we added a pound of weight and distributed it evenly until it reached 50% of its volume submerged. And we ended up getting 8 pounds for 50% submersion, and then we went further and tried 10 pounds, and we ended up getting 60 to 65% submersion. So our theoretical calculations were correct.
So this is an experiment of the sonar sensors, the motion sensors. For simplicity, I did it at 30 centimeters, 20, 10, and then 5. As you can see, each center goes from 30 to 20, 10. Each LED is lit, and you can't see it, but the speaker is going off with this. And just to prove our program.
So one of our initial motivation for this project was the reefs. Currently, people are trying to monitor reefs from irrigation and other stuff. But having a autonomous vehicle that could be there at times where humans cannot, you can have constant monitoring and a live feed of the reef and what's going on there.
For design experience, we learned how to pretty much handle mechatronics with the water system. It was kind of difficult, and we're still learning about it. We also had to learn collaborations. We butted heads with a bunch of stuff, but at the end, we're a team, and we came out as a team, and we agreed on a bunch of stuff. And it was really nice that we were able to use a lot of classes that we learned here, with programming, mechatronics, simulation software, and manufacturing to implement this in our project. So we were able to use the wide variety of classes we took here.
Here's some standards that we used. The top standards are general engineering standards for drawings and drawings and such. IAB standards we use for electrical connections. Mostly the water tech connections we use for the motor and the Arduino. This is the mil-spec connector we use to make it watertight. The IPX6 rating is up to 1 meter submerged, and it should be okay up to there.
So this is a quick cost analysis of our prototype. We were given a budget of 500. We spent 470 on most of the components. So for this further detail in the report. This is our Gantt chart. For the first half of it, we stayed on time, but then we started struggling when it came to figuring out how to put everything together. Breakdown of responsibilities. Jerry was in charge of the packaging and SolidWorks simulations. I was in charge of getting the electrical components and sensors, and Jose was in charge of the programming and the project management.
So in conclusion, we have to get to see an entire engineering design throughout. We started with our initial concept. We moved on to testing each concept individually to see our pros and cons of each concept, and we came with one general concept that we worked on. From there, we ended up with our design. We built a prototype and tested it.
And future work for a big project, we would like to probably add solar panels since this cost can be continuously moving. We have to worry about energy in the motor. We also want, since it's Arduino, it's open source, that means it's highly customizable. And as well, we have to make sure it's also saltwater resistant. And for a small project, we would like to find suitable sensors, because the sensors we bought were really cheap sensors, knowing that it would hard to break, which we did burn a lot of them, as well as making the model maybe a little smaller. And then having it work, because I'm an avid diver, and I would like to just take it out and use it. So as of right now, it probably won't 50-50 chance, but pretty much the future work is to get it working for days, so I can just take it out and throw it in the water.
Thank you. Questions?
You had stated earlier that you wanted to eliminate the tie to the diver. Is there anything in the system that will locate this system relative to the diver?
No, so currently our thought for diving is, let's say you're out with a group expedition, you would GPS pinpoint your reef of interest or a point of interest, and you would throw it in the water, have it sent out, and wait there for you. So it's the diver's responsibility to stay in that point of interest for this buoy. Now, as I said, we have another mode where it circles. So that gives us more of a perimeter where you can have multiple of them at once and try to create a perimeter around a group of divers, or hopefully not by yourself, as you should never be alone.
Did you actually test it in the water?
We put it in the water, we haven't.
We tested the components separately, but since I'm still figuring out the program, I didn't want to wire everything and throw it in the water. I was burning
Not even a
it.
swimming pool? Try?
No, not all the components on, not yet.
Okay.
Just to follow up on that, why wouldn't someone just use a GPS device if they want to just go find a reef? Why would they need a buoy to go there and show
Well,
them?
when you go diving, you need a buoy in the water. So
Right.
this is more for protection for the diver. So instead of having a tie and carrying a buoy, you could just give it a G. Like if you know you're going to a reef, but give it those coordinates and then you throw it off. But
Sorry, you just said it doesn't do that though, right?
it doesn't do what?
You have no way of determining where a diver is.
Actually, I guess I don't understand your question.
So just a minute ago, the question was asked, can it locate a diver, correct? That was the question. You said no, it cannot. Right? There's no system in place, there's no thought of a system for that at all, right? It's not integrated. Then you said the motivation is to go to a specific location and locate a reef or whatever, right?
Yeah.
But then you just said no, but the motivation is to locate a diver, so we're kind of going in circles, right?
No, the motivation is to protect the diver. So the diver's going to a specific reef. You can, when it catches GPS off, you'll circle depending on the program.
Mhm.
Or if you give it the GPS coordinates, if you know what reef you're going to, then you can have it follow a path. So it's not.
So how does it protect a diver? in
I would
that
say
case?
the biggest protection is perimeter defense. So we have our sensors, we have our speaker, we have our lights. As something approaches, you can have a siren. So we have an audible signal, anyone on the surface will hear it and try to call attention.
Okay, so this is completely different right now. So you're saying it's going to go sit by a reef and tell people that you're coming near
perimeter
it.
defense, yeah.
Okay, gotcha.
How does it do that? How does it tell them?
Excuse me,
Do they have a GPS or, one of those
Siren.
smartwatches?
Siren? Obviously, these
When you're diving, what does it do?
Oh no, well
Yeah,
of
right.
course we're thinking of a commercial aspect. So you have a company, you have someone on the boat, and you have perimeter defense of these buoys.
How much range do those sensors have?
But these cheap sensors, they only got like 15 feet. But
So
as
if a boat gets within 15 feet of you, it's going to hit you,
for this,
because you can't
yeah, of
stop it
course.
that fast.
For this, but that's where we're aiming to find better sensors.
I mean, and this is something we both are kind of going back and forth with, but you said something earlier about it would protect a diver from a shark. The question being though, what, is there a certain signal a shark gives off different from a dolphin or a large fish? Or is it just gonna go off every time a big fish?
I believe you're referring to our literature survey. That was just one of the types of smart buoys that we had looked into.
This one doesn't do that.
No, this one doesn't do that.
How does the other one do it?
So what you're doing basically is eliminating the time. That's your
You
purpose.
can't tell the difference.
Okay. So I guess, yeah, you reach your purpose now. The only thing that is that you're eliminating the time, and that eliminates basically the link to the diver. I thought about if there's any way that a diver can carry something that can link
So that was.
without the tie.
That was
but
our original idea. It's just, it's way too hard, and like I was looking into it.
it's just not feasible.
Why is that too hard? What was the thing that got in the way?
It's just, so when you work with,
So with the research on communication on water, GPS was not feasible for us, so we went with low-band radio frequency, and the transmitters we found that were applicable to our project were extremely out of our budget.
so pretty much no company has done it. The only people that have done it is Shark Week, and it's not even fully autonomous, so they have, obviously they tag the shark, right? And then they have the robot following the shark. But actually, so since the shark has the gyro and a pressure meter, it actually pings back to the boat, so then the boat pings back to the robot to get it to follow the shark. So it's not really fully autonomous.
And wouldn't you be able to get an app that people can download on their watch or something?
In what sense?
And be able to receive all these signals?
Well, we like to do the app because they actually have some autopilot apps where you trace out the path, and then those are for RC boats, RC planes or RC cars. So in this case, we're going to be doing RC boat.
One more
Yeah,
quick
go
one.
ahead.
Just when did you find out the price of the transmitters?
Pretty much early on.
Yeah,
That's
so
why we
it's
had to
early
change.
into our.
Okay.
Because like that, I really wanted to follow the diver, but then once you started looking into it, it's just,
Like the average diver wouldn't purchase it.
So when I looked into like the Shark Week, they spent like 400 grand in over like 4 years, and they still haven't perfected it. So. that's
So then
why
you just kept pushing forward, and you just kept saying, let's keep going though?
We're already like, close to the end of our senior one, like halfway through. So
Okay.
that's where we figured out different ways to use it, and not only that, but also for the big picture. You want to protect the reef. For illegal fishing, for illegal dumping, you can have the big picture of it follow around the reef, so that way people come in, take pictures of it. That little extra percentage of protection.
Okay.
You figure it can save us some reef.
Thank you.